Hello again. My name is Javi Molino, and if you're just joining us, you've missed out on some pretty terrific sessions. What we are doing is giving you a little taste, kind of showing you a little bit of the legs, so to speak, of what to expect when you attend a John M. Campbell G4 gas conditioning and processing session. Today we're going to talk about refrigeration, natural gas liquids recovery, and hydrocarbon dew point control. When you attend a G4 session, in this particular chapter, you'll walk away being able to explain how a mechanical refrigeration system works. You'll be able to calculate the utilities required by a mechanical refrigeration system. You'll be able to explain why condensing temperature impacts power requirements. You'll explain how a valve expansion works. You'll describe why turbo expanders are much more efficient than valve expansion, and you'll recognize the cascade and mixed component refrigerant LNG processes. What we're going to do today is focus on a simple mechanical refrigeration system, and I'll take you through an explanation of how a mechanical refrigeration system works. If you joined us earlier, you would have seen this diagram over here when we talked about hydrocarbon dew point control units, and this is nothing more than a representation of problem 8.9, which was our hydrocarbon dew point control unit. Just as a quick review, what we do is we are bringing a feed gas in. This is our rich gas that comes into the system. It's hydrocarbon wet and water wet. It goes through a gas-to-gas exchanger where the gas coming out is now, it's now a two or actually three-phase mix. You have liquid hydrocarbons, you have vapor, and you will also have inhibitor to a rich inhibitor that's injected to prevent hydrate formation. It goes into a gas chiller where we are boiling propane, and we'll come back to that in a moment. And the process gas leaving the gas chiller is at its hydrocarbon dew point specification, goes into a cold separator where we separate the gas and the liquids. The gas then comes out, is cross-exchanged in the gas-to-gas exchanger, and then goes out to the sales gas line. Well, up to this point, we've looked at the gas chiller over here as a simple little box or unit. We've, up to this point, identified that simple chiller as a circle with a little arrow through it, but there's a lot more that goes on in that chiller. That chiller is represented by this circle over here. What you have is you have your chiller, which is this, and you have a compressor, you have a condenser, and you have a surge tank. There's a lot of equipment that is associated with that gas chiller. On a big picture, what you're doing is you are taking warm process gas and you are boiling liquid propane. The warm process gas gets cold, the liquid propane evaporates, hence a chiller is often called an evaporator, and what you're doing is transferring the heat from the warm process gas into the liquid propane. Let's take a look and explore what goes on in the refrigeration system and map it out with a pressure enthalpy diagram. We would have discussed the pressure enthalpy diagram way back in energy changes. But to give you an idea, to give you a review, a very quick review of a pH diagram, is what you're doing is you are plotting pressure versus specific enthalpy on a diagram, and this pH diagram is specific for propane. So knowing that, and knowing that we are dealing with a pH diagram, what we're going to do is take the refrigeration system that we see in the circle over here, and we are going to locate those letters on a pH diagram to help explain how a simple mechanical refrigeration system works. So let's pick a letter, and we'll pick something simple. Oh, you want to pick A. Well, that's a good letter. A is, first thing we have to ask is, what is A? What kind of fluid? Well, if you look at it, A is a saturated liquid or a bubble point liquid. So let's locate A. We know that it's coming in at high pressure and it's a bubble point liquid. Well, here is my bubble point curve. So point A has to be somewhere on that bubble point curve. And we know that it's at a high pressure, so just arbitrarily we will locate point A on the bubble point curve at high pressure. Pick another point. You say C. I like C. C is a dew point vapor. The dew point curve is this is our dew point curve over here. So what we need to do is locate the dew point, and point C is going to be on that dew point curve, and because we've passed through a control valve, we know it's going to be at a low pressure. So this is going to be arbitrarily point number C. Once you've located your points A and your point C, you have defined your mechanical refrigeration process. Let's take a look and see. When you go from A to B, what you're doing is you are taking an isenthalpic expansion. That's an expansion across a valve where your change in enthalpy does not change. Your delta H is equal to 0. So following the path from A to B, we're going to go straight down. This is going to be our JT valve, which is over here. And we're going to drop that pressure to the same pressure as point C. In this particular example, I'm assuming no pressure drop. You couldn't read the pressure drop on a pH diagram anyway. This is point B. So I've just taken a pressure drop through the JT valve to point B, and you'll notice that in this pH diagram, I am a two-phase mix. I have vapor and liquid at point B, which is indeed the case. I then go through the chiller. This is my chiller, and I'm going through the chiller. I'm boiling the propane. I end up at point C, which is a dew point vapor. I now take point C and I feed it into the suction side of a compressor. When we compress, as we learned in chapter 15 on compression, we follow a path of constant S. So I go along a path of constant S. This is my compressor. And I compress it up to a point D. So here's my compression path. These are lines of constant S. So I'm following a path of constant S for my compression. I get to point D, and then what I do is I go through my condenser to condense the pressure, the high pressure vapor propane to a bubble point liquid, and I start the cycle all over again. The question I have for you is, what determines the discharge pressure of my compressor? When you attend a G4 class, we go into discussions of that nature in great detail. We also talk about how your condenser temperature may affect the performance of your refrigeration system. The next time we get together, we are going to talk about TEG, triethylene glycol dehydration systems. I'll see you at that time.